Okay, good morning, everybody. We are going to get started here this morning, and I want to thank all of you for joining us. I know for some of you, as I'm looking at your names and I know where you live, I'm thinking there's more than just Ken joining us at 2 a.m. So sorry about the time frame. Trying to match up around the world to all of the people that use a lot of these instruments and need a lot of the updates that we may have today for you on the chemical warfare threats. Just the timing can't meet everybody. So we are recording this session. So for those of you who would like other people on your team to review it, or for those of you who can't be on for the whole time, we will have this recorded. And following up after the session, we will send you a link to some white papers that are covering topics that we discussed today. We'll send you a link also to the video on the ProEngine YouTube channel. So all of those things will be available to you after we're done. So with that, my name is Christina Baxter. I own a company called Emergency Response Tips. Prior to working with Emergency Response Tips, I worked with the Department of Defense and what was then known as the Combating Terrorism Technical Support Office. So I have had the luxury of working in this area for the past going on 30 years now. So I will be presenting a lot of the operational side of this, and then my colleague Scott will be presenting a lot on the detection side of it. So Scott, if you want to introduce yourself.
Sure. Hi there, everyone. My name is Scott Hartley. I am the CEO of ProEngine, so I basically run the U.S. operations here. So our main facility is in Florida. I'm presently in Northern Virginia. We have employees across the country and one in the Midwest and a couple on the West Coast, just to let you know that, as well as colleagues all over the place in different countries. So, but I appreciate the opportunity to be able to talk to you about what I think is a very timely and important topic, especially in today's global environment. And so hopefully it'll be beneficial to everyone.
And for those of you who were on early, if you have questions throughout, everybody is on mute because there's a lot of people online and it would be very hard to figure out who's talking. So there is a questions area on the interface for GoToWebinar. And so if you have questions, please feel free to type them in. I will try to watch that as we present and we'll go from there. So we're going to turn our webcams off and then we're just going to focus on the slides. And Scott and I just kind of do a team teaching approach. So we'll be going back and forth throughout. So if you hear the voices change, that's just the way we like to teach with one another, to be able to add on to what each one's background and operational experience is, to try to give you the best round out of what we have to offer today. And obviously we won't be able to answer all questions because some of them we'll have to look up, but we will get back with you for those that we can't answer. So with that, we'll start out. So I'm going to turn off my webcam. Okay, so the topic today is going to be risk-based response to chemical warfare threats. And as you are all aware, we are in a rapidly changing environment right now. So I want to just start out with, where are we in the threat spectrum? So for instance, this is the USA approach to threats right now. And I can say that from a USA perspective, we really aren't worrying about a lot of elevated threat today on chemical warfare agents in use in the United States. We do still see a lot of those easier types of materials. So maybe things like the toxins, ricin, abrin, nicotine, botulinum, all of those types of toxins, we see those quite often in the United States. In terms of toxic industrial chemicals, the binary devices, or the easy to access, easy to make, but being binary in form, they're easy to transport to the target areas. So hydrogen cyanide, phosphine, hydrogen sulfide, chlorine, things that can be made on the fly. In terms of chemical warfare agents, the only one we see a lot of chatter about in the US is really poor man's sulfur mustard that you can make with things from Home Depot. We really have an elevated threat from synthetic opioids, mainly due to the high availability of the materials. The good news on that front is we have dropped down considerably in the purity of synthetic opioids that we're seeing. So if you went back even 2 years ago, we had a huge amount of synthetic opioids that were very high purity coming in directly from China. And as that route has been quenched quite a bit, now most of our material is coming up from South America, which means that it also comes in cut. So we end up having materials that are no longer at that 97% and higher purity. They're at that 9% and less purity, which means that that threat of an intentional release has dropped drastically, which is fantastic information. Now, while we do talk about the Novichoks or the A-series agents, and we'll talk about them some today and show you some new information, we don't see an elevated threat for their use in the United States right now. They are very much still being held and used as a targeted assassination tool, and we'll get into that a bit further. Now, one of the things that we have to worry about is reality is, even back to 1995 with the Shrinkyo cult's release of Sarin in the Tokyo subway, that was really the in modern times, kind of the defining moment where somebody had used chemical warfare agents after the signing of all of the agreements saying that all of the main powers would not use these types of materials. But now fast forward to the last 10 years, and we're going to go into a few of these, we have seen an increased use really since the civil war in Syria. And so when we saw in Syria people using a variety of different materials, including chlorine, including mustard, including sarin, those types of things were used and confirmed by the OPCW. Fast forward now, and we have had several different events with VX used by the North Koreans. We have had several events with the A-series agents used as target assassinations by the Russians. So we are now at this point in time where it is becoming kind of in vogue to use chemical agents again, and that is quite scary. Now, when we look at this instead from the European approach, because of everything going on and the heightened sense of threat in your area, mainly due to the ongoing war in the Ukraine, we have to worry about those same things that we had as the US threats, but add in the elevated threat for pharmaceutical-based agents and fourth-generation agents, as well as the elevated threat for mustard, sarin, and VX. And when we look at those, we have to remember that all of our militaries are creatures of habit. Things that they've done in the past are things that they're likely to do again. And as we look at these things throughout this morning, just remember that there are a lot of different materials available, but the ones that we're most concerned about in the front right now are mustard, sarin, VX, potentially A-series agents, and then some of the pharmaceutical-based agents just from past history. The toxins, again, readily available in the arena, but not necessarily talked about from that perspective. Now, we have to remember that NATO also warns that due to the Russian pretext for using chemical weapons, the ability of them, they've been talking a little bit about this false front of saying that the Ukraine and the US have been using biological agents and producing them under the guise of public health, that this is now, from past experience with the Syria campaign, a potential warning that chemical weapons will be used. Now, just to get back into the history of chemical warfare agents, there's a variety of different terms we have to understand. And I know I brought a few of them up as we went along. But as we look at the generations of chemical warfare agents, there's a lot of things that change over the years. So when we started with that first generation of agents, and you'll see on the top in green are the anti-personnel agents, in the bottom in red are the area denial. Area denial are types of agents that tend to stick around longer. They have lower volatilities. They are materials that stick close to the ground. Whereas some of the anti-personnel agents are materials that tend to loft up higher. They may be gases, they may be vapor-forming liquids, or in the case of the pharmaceutical-based agents, they tend to be electrostatically charged solids. But as we come along, the first generation of chemical warfare agents, very much choking agents, blood agents, the chlorine, the hydrogen cyanides, those things that were very volatile. They did their job, they went away quickly. In the area denial, we had the blister agents. So while they were thick, oily liquids, they still produced enough of a vapor to cause a problem. As we got into World War II and the second generation of agents, that's where the G series nerve agents started in. And then later in, we got to those V series nerve agents, which actually are much thicker and stickier. To get to the third generation was actually taking those same materials, not producing anything else, but coming up with methods for storage and production that left you with two materials that, when stored separately, had long shelf lives. But then when put into a munition with a pre-charge detonation, you would have a mixing of those materials so that you didn't have to worry about long-term storage of those threats. And so that's where the third generation is. The only difference between second generation and third generation is the way in which they're stored. Second generation are stored as the final product, whereas third generation are stored as two precursors when put together become the third. So reality is we don't see second generation agents anymore. We see third. Now, when we get into that fourth generation of agents, which is the FGAs or the A series agents, those are, again, oily liquids and solids that tend to be area denial types of materials. Definitely all of these materials are really optimized for targeted assassinations or for keeping troops from going through an area. In parallel, we have the pharmaceutical-based agents, which are generally chemicals and materials that have a dual use. They started out as things that were perfectly suited for anesthesia. So most of these things are either breakthrough pain medications or anesthetics, but they have illicit use. They have a very required use in medical community, but when used in an illicit way, become a hostage-taking tool or something that could be used for targeted assassinations. So as we go forward, when we talk about the generations of agents, this is where we're going. And remember that we start with things with very high volatility, and as we get further into our fourth generation, we have things with very little volatility. Or we started with gases, moved into vapor-forming liquids, and then moved into liquids and solids. And so that's been the progression over the years, is starting out with things with high volatility and getting to things with less volatility. That brings us to a point where we end up in this fourth generation and pharmaceutical-based agent area where we have to be able to detect, sample and detect aerosols, because most of these materials are now either liquids that have very low vapor pressure or solids which have generally no vapor pressure involved. And so they're dispersed as an aerosol instead. And that brings us into a detection realm, which we're very unused to. So let's go into a few of these things here. And I want to bring up one other area of what are we trying to measure and why? And this is something that becomes really important, especially as we communicate with the companies producing these detectors of what are we going to use it for? So when we get into that early detection of chemical warfare agents, we need to be able to detect at exposure standards. So something like the occupational exposure limit, the time at which if we use that material and was in constant contact for 8 hours, what would be the effects, okay? And then we get to that immediately dangerous to life or health, where a 30-minute exposure would cause, even if it's an inability to evacuate from the area. So that's that next level. And then, of course, that lethal concentration low, where we would expect children or elderly to become susceptible to the lethal concentration. So not quite the LD50, where we have that lethal dose where 50% of the population will die, but that LC low, which is the concentration at the low end, that people are going to start dying. And we use these things for not only from an operational perspective to determine where we are going to do for protection. So are we going to put on our SCBA? Are we going to wear chemical protective clothing? Each of these things is very important, but also, are we going to evacuate or shelter in place? And what decisions are we going to make based upon that? When we get to those higher types of detection, where we generally are doing an identification, that's when we start talking about Raman spectroscopy, infrared spectroscopy, some of the mass spec things that take a lot longer to use, but can provide a unique identification. And so from my perspective, in an operational context, trace detection is detecting to warn people, evacuations, those types of things, and detecting to protect my operators. Whereas bulk detection technologies are using detect to identify or confirm what we had figured out in the earlier stage. I'm going to pass it over to Scott so he can talk a little bit more about this.
Yes, and from a detection standpoint, kind of the way that people like to look at these to delineate between your trace and your bulk are ones that you're comfortable with or that are commonly brought down range, so they're brought into the hot zone, versus the detectors that you like to keep on the safer side of on the gray zone or the totally clean zone with that. And so some of the delineators between those technologies are just your ability to easily handle them and carry them. So they tend to be lighter weight, more fit into your palm, or can attach to your uniforms with it. They tend to obviously probably be a little bit less expensive too, because if you are bringing it to the hot zone and it is a very nasty chemical, sometimes you can't guarantee that you can fully decontaminate these detectors. So therefore, you don't obviously want to bring in a $250,000 detector or $100,000 plus detector into there. And then the second thing is more of the response time with it. So a lot of the trace detectors tend to be continuous detectors, where they're sampling continuously, or they're just sitting there constantly looking for the response to come, or looking for a threat material. And then the other thing that comes with them is just a quicker response time, because a lot of times when these types of trace detectors are being brought into, they're doing the detect to warn aspect of things. So you may not know where the source of the materials are or where they're located, and you're trying to obviously determine concentration levels to understand, where are the unsafe levels. So are we talking below your occupational exposure limit? Are we talking above PEL levels? Are we talking above IDLH? To hit on those, so your ability to sample these or to get a response back on what we're seeing very quickly is important. And that's one of the delineators between that versus bulk detection systems, which tend to take longer to do those analyses. But the bulk detectors tend to provide much less false positives or have cross sensitivities. So with that trade-off with response time can sometimes be those aspects of cross sensitivity that you need to take into consideration with them. And so that's why you need both trace and bulk detection methods in order to do your full response. You don't ever rely on just one detector, and there isn't one detector that gives you all the information that you need as well. So anyone that ever sold you on that is not telling you the truth.
Coming from the vendor himself.
Yes.
Okay, so what I did is put together just a few different reminders of each of the different types of materials that we've come across, and what would we do operationally and what the solution step might be. So for instance, the pictures that I'm showing right here are some chlorine cylinders that were actually dropped into a residential area in Syria in February of 2018. And in this case, there were many people that were affected. You can see here, just in the picture on the bottom left, where the materials came down, and you can see the grass all getting killed and yellowed here. But with it being chlorine, this sticks close to the ground and moves directly into the area of where they were trying to target. Now, chlorine is one of those materials that is very hard to detect with a lot of our traditional chemical warfare agent type detectors. So this is one where we generally go back and use our electrochemical cell. So I just put an example. I've always used the Ray systems sensors. So the electrochemical cell from Honeywell Ray for chlorine can give you the range of operations that we're interested in. So 0.5 from the threshold limit value. So that's that 8-hour workday exposure where you're not going to have long-term symptoms, all the way up to 50 parts per million, where we're likely to start seeing susceptible populations having long-term health effects or even death. And it gives us a 0.1 part per million resolution. The biggest problem with it is that you have to, your T90 or the response time where you would read the reading is 30 seconds of continuous monitoring. So you would want to have that cell there and leave it in place for 30 seconds. So this is one of those things where you might want to consider some type of remote deployment of the sensor to ensure that you can leave it in that place for 30 seconds in a very corrosive environment to get you the information you need. Now, in terms of some of the first generation agents, Syria had a couple of different releases of sulfur mustard. And so Maria was one of the ones. And if you look at the picture to the left, this one came from one of the OPCW reports, that there were several different interesting events where they were able to get a yellow powder resolved from some of these, which could have been just sulfur, but they also were able to get a oily black liquid and several others. And all of these red points are projectiles with toxic chemicals, but not all of them being sulfur mustard. So a lot of them were chlorine and others. So when you start looking at this and then look at the munition here with its black tarry-like substance, we start looking at sulfur mustard. And remember, we often hear people call it sulfur gas. It is not a gas. It is actually a vapor-forming liquid. And while it does not form great vapor pressure, great levels of vapors, it does provide quite a bit. In this case, 50% of the projectiles that landed there in September were laden with chemicals, and that's quite scary. When we look at that, the good news with sulfur mustard is we have plenty of ways to detect it down into that operational range. So when we look at this, we want to be able to detect down at about 3.5 parts per billion or 10 parts per billion when we're talking about areas of operational relevance where we know that the people exposed will be able to come back and have very successful livelihood afterwards. Whereas when we get out to that 0.32 parts per million or 320 parts per billion, we end up at a point where these people, some of the susceptible populations, are going to have long-term health effects or even death. So in this case, we have the AP4C sulfur channel, which will detect all the way down at 76 parts per billion and upwards. So we're able to get down to the areas of interest with a 2-second response time. We also, for those of you who have the MX908, that can measure at 3 parts per million, so a bit above the high level of interest, but in vapor mode with identification. It will take minutes for it to get enough sample for it to give you that unique identification. LCD 3.3, so an ion mobility instrument, will take about 2 minutes to get up to that lethal limit of continuous monitoring. And then the M256A1 kit, which is more of a colorimetric type of approach, will take about 15 minutes in that area at the lethal limits to be able to get a response. So we do have a lot of solutions. We just don't have a lot of fast solutions that can give us that near real time outside of that AP4C.
So what you see here, and we're going to give examples of it for each of the main chemicals as we go through there, is the display system for the AP4C. So what the detector would actually be demonstrating to you as a user of the equipment with it. And to just give you the quick overview for those that may not be familiar with it, so the AP4C is a flame spectroscopy machine. So what that involves basically is we use an energy source in the form of a hydrogen flame, but it could be in other types of things. And what we do is we excite the materials that are coming through the detector on it in the airstream. And what happens is you excite those materials, they start to move around, get all excited. And then when they go past it and they relax, they actually release light. And so we capture that light and then we analyze the light and we provide outputs for it. So we're looking for core materials that are found in these chemical warfare agents. So the advantage of flame spectroscopy is you can actually get to extremely low sensitivity levels with it. And we do have the accuracy of spectroscopy from the standpoint of unlike some other detection technologies where there can be false positives where it could say, hey, you're seeing a nerve agent, but it's really not a nerve agent, it's some other material, or it's not cross-sensitive like you see with a lot of your single gas meters where it's cross-sensitive to a bunch of other materials simultaneously. So you have to understand what those are and what you're dealing with specifically. So it's a little bit different. In this specific case, we're dealing with sulfur mustard. So sulfur mustard will hit on the S channel or the sulfur channel. So we're looking for the core material being the sulfur in the the mustard gas to be able to do that. And so, as Christina has said, we're about a 3-bar exposure level at the lethality, really even at the TL3 level of, so we can see there in that case is 0.32. So from the standpoint of available detectors on the market, we are very sensitive, as you can see from the available data for other types of detectors that were there. We're pretty much an order of magnitude more sensitive, or if not more than that, in order to be able to detect. And the additional advantage, since we're looking for visible light that is coming off these materials, we're sampling continuously, so we're telling you what went through the detector every 2 seconds with it, so we can have a very quick response time with these sort of materials.
Okay, so when we get into those 2nd generation and 3rd generation type agents, I'm going to talk about Sarin just for a moment. And in this case, it was 1995 was the last time that we had a Sarin attack that really made its mark around the world, and that was with the subway attacks in Tokyo. But in terms of Syria, there were several cases where Sarin was used and confirmed by the OPCW. And in this case, Sarin is one of those materials that at ultra low levels will start to affect you. So as you can imagine, when it comes to guidance on what you can be near at a regular work day, so that 8-hour TLVs and the IDLH levels, those are occupational exposure standards, and those levels are going to be ultra low because we don't allow any exposure really during an occupational event. Now, the TL3, or the area where we're going to start to see those long-term hazards, is going to be only down at 22 parts per billion. So we need to be able to measure at very low levels here. The good news is that the AP4C phosphorus channel is extremely sensitive. And one thing to note on the AP4C for those of you who are users is that each one of the channels, whether it be the phosphorus, the nitrogen, the sulfur, or the arsenic, has its own independent limits of detection. So if you have a chemical that we'll see that has different elements within it that are able to be seen with the AP4C, you're going to have several different limits of detection applied across the different channels. The other one to keep in mind is the MX908 can measure all the way down at 6.9 parts per billion in vapor mode, but it will take about 2 minutes of sampling before it gets enough material in to create that spectral resolution to give you an identification. The LCD 3.3 is targeted to measure down at some of these low levels as well, so it will get down to IDLH if you leave it running for about 30 seconds in the environment. And it'll get up to the lethality limits when you are at about 10 seconds of measurement. And similar to the M256A1, the colorimetrics, it can get down to very low levels with the colorimetrics if left in time in contact continuously with the agent for a length of time. So we have a lot of different ways to measure Sarin, but one of which is the AP4C.
So continuing on the discussion relative to what the detector would see. So because Sarin is organophosphate, you are going to hit on the phosphorus channel first and foremost with these. In the case of the phosphorus channel on the AP4C, we set the detector to be as most sensitive as possible. So that's how we are able to get down to that 1.6 parts per billion detection range for the system with that. And each channel is independent, as Christina was talking about. And the reason why that is because the threat profiles for the materials are different. So we just didn't want to be triggering all the time. What we do is we set the trigger threshold for the most likely or the most caustic types of materials that we're dealing with, which in this case tend to be your chemical warfare agents with there. So you can see that we start to detect at that 1.6 billion parts per billion. And so at IDLH, we're giving you about 2 bars. At the lethal amount, we're giving you 3 bars with there. So it is a good instrument to bring down range. It's the only one that is sensitive within that range. Obviously, because some of this happens in meiosis can occur at your parts per trillion. It's really hard to get down to parts per trillion if you understand even parts per billion versus parts per trillion, even parts per billion versus parts per million is a pretty big drop to be able to do that. It still gives you the information that you need from that, and you can actually make decisions with us ahead of time. The other thing about sarin is it tends to be an anti-personnel weapon because of its vapor pressure being higher than some of the other materials. And we're going to talk about vapor pressure a little bit later in this and why understanding vapor pressure is important from a detection standpoint for these materials.
Okay, when we get into that third generation, and this was actually a fabulous example, I guess, from a CBRN operator perspective of an example of how modern day use of a binary weapon could be employed. And in this case, it was the attack on Kim Jong-nam at the Kuala Lumpur airport, where two different people applied materials to his face. And he ended up succumbing to those materials, which produced VX in real time within about 20 minutes of his exposure. Now, the good news is that VX, when made there, is very low volatility. The bad news is it has a very good skin permeability. So reality, he was affected in his face, which would have been a pretty quick permeation, and likely also had the slight amounts of vapor produced would have been inhalable or enter into the eyes and nose as well. So when you get to something like VX, you're now talking parts per trillion levels of interest and parts per billion levels of interest for IDLH and getting out to those lethal limits. So when we're talking about levels like this, we're talking about a material which, unless you are right on top of it, is not going to produce enough vapor for you to have an exposure. So good thing about this is if you're standing up and there is not huge amounts of this aerosolized versus vapor phase, then your likelihood of you having an exposure from an inhalation perspective are very low. So when we start looking at this, again, we have our AP4C phosphorus channel, which is going to give us our almost real-time measurement. We also have the MX908 again, which can measure in vapor mode for these at 31 parts per billion after it takes just a couple minutes to build up and give us that unique identification. The LCD3 3.3 will take about 90 seconds to get up to about 4 times that lethal limit. And then the M256A1 will take about 15 minutes to get up to about 2 times the lethal limit. So we're talking about areas that are going to be relatively low, but take quite a significant amount of time, with the exception of the AP4C for detection and the MX908 for identification.
So in the case of VX, it is more an area denial weapon. So as Christine stated, it's going to be closer, most likely, because it has the phosphorus in there. It tends to be heavy. It also tends to be very caustic and doesn't want to move, and it's also very thick. And so it will tend to be closer to the ground unless it's purposely put on either a person or on a certain thing that humans will be touching often with it. So in those cases, you'll most likely get a gradient of the material. So closer to the source, you'll get some off-gassing of that. And so we are able to detect that, but beyond what the lethal area for these materials are, just because they are so, it doesn't take very much. So these are one of the things that you see with your chemical warfare agents as you're going from your second to your third to your fourth generation, is that they're becoming more and more toxic. So that, you know, all of these materials are all the nerve agents are organophosphate-based materials, which are modified versions of pesticides and insecticides, and they're just engineered to work better against humans. And so as we get better and better knowledge from a scientific standpoint of how these work and what we can do from chemical structures in order to make them more effective, what you're seeing is less and less materials are able to have a drastic impact on the human. The good news is, because of the nature of VX, and we'll see soon with the A series as well, is that they don't want to off-gas very much. And so what that means is they will stay around for long periods of time, but it also means that the likelihood of it being in a vapor threat that then gets into your respiratory system is a lot lower. and you will tend to have gradients as well. So it'll be much closer to the source of the material. So that's one area where VX differs from Sarin. Sarin is very easily aerosolized, and it has the vapor pressure doesn't last very long, and so it'll tend to be aerosolized and in the airstream and up higher where we're breathing in, versus some of these which will tend to be closer to the ground or where they're applied. And so that's one of the bigger differences with them as well.
And this is something that you could see really importantly in that Kuala Lumpur airport incident. If you watch the videos and realize that, while Kim Jong-nam died within 20 minutes of exposure, all of those other people working around him and providing him support and wearing gloves, none of them seem to have any type of difficulties. And a lot of that is due to the fact that you can really be around VX on a surface or on another person, and unless you interact with the material itself, that transfer does not easily occur. What I do want to bring to point here is that while the lower end is the 1.6 parts per billion, it is just barely higher than that low level of lethality. Now, as we get into the 4th generation agents, in terms of going into operationally relevant numbers, I can't really give you much here. So in this case, we generally just stick with the A series agents numbers. Okay, so we're talking parts per trillion and parts per billion still. But we're talking about a series of agents that have not been fully characterized. In this case, we talk a lot about the A230, 232, 234, but we very rarely talk about all the other potentials. Structurally, there are about 300 to 400 different A-series agents of interest, and we have to spend more time characterizing them and getting that material out and about where we can use it. But for now, just remember that when we're talking about their toxicity is most similar to VX. And so in lieu of having the exact numbers, use your numbers for VX, okay, and apply it that way. Now, I think most people, when they think of the 4th generation agents, you think of the attacks in the UK and the targeted assassination attempt of Sergei Skripal and his daughter Yulia, which ended up expanding out to others as well. Charlie Rowley, Don Sturgis, each of these people ended up with an effect from that event. But reality is the most recent event that we have that has been confirmed by the OPCW is the August 2020 attempted assassination of Alexei Navalny. And in that case, they're talking about it being a material called A262. And again, these materials generally have phosphorus, which makes it rarely detected at low levels, but also have nitrogen, and some of them have sulfur. And so when you start looking at that, you have a broad range that is detectable based upon the different types of materials. But remember, in this case, you have to be able to measure very low volatility materials, or you have to be able to measure aerosols. And that's where you start to see your limitations on the number of instruments that can be used here. So in this case, the AP4C, just like we have with VX, can measure in vapor phase with a limited detection around 2 parts per billion. But the actual time for detection takes a little bit longer because these materials are so heavy and tend to be so oily that they slowly move through the system because they start to get stuck on the sides and slowly make their way through. So we have to remember that we can get them in there, but we might have to wait a little bit longer than we did for other materials. So that 2 seconds comes out to being 10 to 30 for our worst case scenario. And we'll show you a little bit more about that. Now, in this case, we're going to measure, if you're just looking at particulates that have deposited, you can get around 25 picograms in the particulate phase. So that's very low, and it allows a little bit more information there. And this is all without going over to the liquid solid phase. We're still talking vapor phase here in the AP4C. But the MX908 can also measure your AC series agents at low levels, but it does require the use of the thermal desorption mode. So you have to go and take a sample, put it in the system, and then let it thermally desorb off. But again, A series agent, low level, unique identification. So just remember, though, that structurally we're the same type of thing as we were when we started dealing with the fentanyls. We had about 1,500 analogs for fentanyls that we had to worry about, whereas here, structurally and toxicologically, there's about 300 to 400 different ones that we'll be worried about in the A series as we go along. Now, one of the things that we have to remember also is that the A series agents are not new. These are something that stemmed from the late 70s, early 80s. And it wasn't until the accident in the laboratory with Andrei Zalesnikov in 1987 that became evident in news media in 1992 that really more information was known about these and started to make its way through the system. The targeted assassination of Ivan Kavalidi and the subsequent death of his secretary, Zara Ismailova, in 1995 really did not become common knowledge. At that point in time, people knew that they had passed away, but there wasn't knowledge or release of information saying that it was specific in A-series agents. They just said that it was a organophosphate type weapon of indeterminate origin and in high classification. The attempted assassination of the Gabrevs in 2015 was the first of the more modern times where we start talking about the actual release of an A-series agent. Now, this is the only one that is a little bit different, where we don't have OPCW testing to confirm the actual material. Now, as you come forward to the incident with Sergei and Yulia Skripal, as well as Don Sturgis and Charlie Rowley, the OPCW, as well as Porton Down and others, all were able to determine the material involved was 100% an A-series agent. Same thing for the attempted assassination of Alexei Navalny in 2020. You still, just in the matter of the last few years, we've had several incidents where this material, which we hoped over the years would never come out of the laboratory, has indeed become the threat du jour or the targeted assassination material of choice for some of our countries around the world. So just note that there has been a significant escalation in its use and its taking out of the laboratory. In this case, in 1995, it was not a sanctioned release of the material, we'll just say it as that, whereas these later ones were believed to be more of a sanctioned approach. Now, as we talk about these materials, a couple of times we've talked about area denial and anti-personnel. And I just want to remind people as we go into this next section Scott's going to talk about, that as we look at persistent chemicals and materials with high vapor density, we have to remember that while they tend to stay in the environment a long time, they also tend to stay in your detectors for a long time. So if for some reason you were to detect what you believe is one of these types of materials, just remember that it's going to take you a lot longer than you expect to clear down that instrument. And we'll show you that in just a moment. But in terms of A-series agents, we expect that their vapor density is going to be around 9, which means that you very rarely will be able to detect them above the threat material. The chances of you detecting them at all is going to be right beside it or with some type of headspace analysis where you've able to create a headspace around the material. So let's come down and show you this in real time. So Scott, I'm going to start your video and then I'll let you go from there.
So what you're about to see is some testing that we recently did at MRI Global. So we knew that we had a feeling that it would work, but we wanted to actually do it in a laboratory environment. So what you're going to see is we exposed the detector to A230, A232, and A234. So if you look in the video that you're about to see, where the blue top of it is actually where the vial of the A-series agents are held. Because these materials are very dangerous, a lot of precautions were taken at MRI to make sure that it was being done. And so there's a huge amount of venting that's going on in these materials. So what we try to do is keep the material at a constant temperature. So you see a little bit of a sand and a hot plate under there. So we kept it at the 25 degrees Celsius in order to do that. And all we're going to be doing is releasing the top of the cap, and then you'll be able then moving the detector over and then timing the release of it. So what we're trying to do is just determine how quickly we can detect it and if we're able to detect it and the different variants with it. Now, as Christina said, there are different variants of the material, and even though they're all under the classes of Novichok's, they can have drastically different vapor pressures, and so as a result, the detection levels are being able to be done. So if you look at literature that has published data for the vapor pressures, you'll see a variety of numbers, and sometimes they don't fully agree. But as a general rule, the A230 and the A232 have the vapor pressures which will be seen faster than the A234. And so the test data that we have validates that. But what you're seeing here is just how quickly it's responding. And so you get some variability in the response time with it. Now, we aren't doing an exact instrument where we're trying to direct all of the vapors up into the detector. We're just trying to sense it, and there is some space from the top of the nozzle to where the detector is. Obviously, you don't want to rub at the top of it and potentially get any cross-contamination, but it shows in kind of a real-world environment where there is agent that's down on the ground or on a surface that you're trying to sense. This is very similar to that, and you're able to detect it at these very low levels. So one of the advantages of the AP4C is just our ability to see these at really, really low concentration. So you're talking at less than your 10 parts per billion, maybe up to most of about a 15 parts per billion exposure level that you're seeing with these. All of the agents did receive we got up to 2 bars on that, which bars are indicative of actual levels or ranges with them. Now, we do store the actual part per million or part per billion range on the device. We just weren't able to download it in this case because the whole detector was exposed. And you obviously have to tread cautiously when dealing with any of these materials because they are extremely deadly and dangerous if not cross-contaminations and other things occur on there. So we weren't able to access the actual physical data that's on the detector, but we are able to get the indicative from the videos that you're seeing on there. And you're seeing with the A234, as we talked about, there is a longer response time with these materials. One, because the vapor pressure is like basically half of what the other ones are. And so that tells you it just takes longer for it to develop and to release enough materials that we're able to be seen, or it takes a while for it to go through the detector system with them, and then also to clear out. So organophosphates is a general rule within the detector. They take longer to clear out than other materials do, just because they're very heavy. They tend to stick in the detector as well with it. And then we probably don't really need to go over this, but just to show the clear out time for these materials. So they all cleared out of them fairly quickly. The longest is 1 minute, 56 seconds, but most of them are less than a minute to be able to do with it. And this is an exact science. We clear out, but just to show you, it comes out fairly quickly, but more so takes longer than a lot of other technologies do.
And so one of the things that I found so fascinating about this video was the fact that we were able to get at room temperature agent high enough to be able to measure. And so to me, that was really a great thing to be able to see, and one that we wanted to get on video to be able to show people that these agents are able to be detected at ultra low levels. But the good news is that even with it sitting there for a length of time, you weren't getting huge amounts of vapor up. So hopefully not to a point where we're going to have to worry about any type of lethality just from it being there at room temperature. Now, remember, vapor pressure is very much affected by temperature of the environment you're working in. So if you're working in cooler environments, all the better. You're going to get less capability to be able to detect it. But if you're working in very hot environments, like some of our friends, we have some of our friends from Iraq on here today. When you're working on some of these environments, just remember that when the higher environments, you're going to get a much more vapor coming upwards. Still remembering, it's not going to go too far. Now, when we talk about the pharmaceutical-based agents, that is also really important here. And another one that we have seen used by the Russian Special Forces back in 2002 with the Chechen theater crisis. Now, in that case, we do have some information on levels of interest. And so operational exposure limits, again, remembering these materials are 100% aerosol-based threats versus a vapor threat. And that's a very different type of material because remember, with an aerosol threat, it's not temperature dependent. It's more dependent upon the humidity and environment. So the higher humidities have less of aerosol, as well as the electrostatic effects of the molecule itself, as well as the dispersion technique. And so when you start looking at that, there's a lot more interest as you go into those aerosol-based threats. The only two detectors that we have today that are able to focus on those aerosol threats in real time at these low levels is going to be the AP4C and the MX908. Remembering though that the MX908, you're going to use your aerosol interface and that will automatically thermal desorb off, which is pretty cool to measure with if you haven't had a chance to see that one yet. Or the AP4C in the nitrogen channel, which while it is its least sensitive, it is still sensitive enough for us to measure in that 2-second time frame. So I'm going to pass this video over for Scott to show because it's very cool on seeing how it works with aerosols.
So what we're going to show you is a video of, so this is fentanyl and methanol mixed together. And so it's at a 1 milligram per milliliter concentration. So the methanol we don't detect. So we're detecting pure the fentanyl in here. And you see, actually, when we did this testing, I was actually really surprised at how quickly it showed up on the detector because we were just dropping, not from high up, but just dropping it on the plate. And the aerosolization or the van der Waals forces just from that dropping were fairly significant. We get up to 3 to 4 bars of a response in the detector, which is a fairly significant response to be able to do that with it. And so one of the challenges with your fentanyl, or one of the things that have to do with the fentanyl that's of concern is, it's not hard for someone, if you wanted to find fentanyl, especially in the United States, you can find fentanyl or carfentanil with it. If you know a little bit of chemistry, all you need to do is find a solvent that it's soluble in. In some cases, that could even be water, depending on what version of fentanyl you're talking with. And now you just need to get an aerosolization method, and now you have a chemical warfare agent. Thankfully, terrorists haven't been necessarily great at chemistry, and so therefore they haven't done this, which I'm very thankful they haven't. But there is risk associated with that, and in those applications of being able to be seen with it. Is it still running, the video? Did it slow?
Sorry, I hit it when I tried to respond to a question.
Okay. All right. So there you see just another droplet, and you can see the response with the device. So it goes up to 4. It clears out fairly quickly with it. It's only a matter of a couple of seconds. So it's telling you what's in the detector at the time. And then we're also doing another example. So we have a hot plate there. And what we're doing is a mixture of acetaminophen and fentanyl. So there's more acetaminophen in there than there is fentanyl. But you're seeing the response of the detector. So I'm actually the one holding the detector in this video, and I didn't do the best job. So I apologize for that, but you can see that there is a response on the detector. So this would be indicative of what happens if you wanted to thermally introduce those into the device. So if they're in powder form and they aren't off-gassing, by heating them up, you can release the materials and be able to detect them with it. So all of your opioids have hydrogen-nitrogen bonds in it. A majority of your pharmaceutical-based materials have hydrogen-nitrogen bonds in them. And so we're able to detect them with the AP4C in those type of environments.
And Scott, I want to answer a couple of questions that came in because they're really relevant to this type of thing. And mainly they both go back to the A series video. And one was from Dion out in Seattle. And she wanted to know how much agent was in the conical tube. And I believe we're not allowed to say the amount of agent that was in there total.
Yeah, so we weren't. Yeah, the answer to that question is we weren't told the exact amount for each one. So we don't know. We know that they weren't the same for each of the three cases for one. But we were given an indicative of 5 milliliters plus or minus 20% or 40% with there. So you can draw the question of like 3 to 7 with it, but they can't release the exact amounts of agent because they don't want people to know how much they have. But that was the range that we were given for those. So not a great amount, milliliters range.
And we also have to remember that the range was in parts per billion between, they thought between 5 and 18 or so parts per billion, what the headspace would be based upon their measurements of the vapor production. And
Correct.
knowing that we were, 2 parts per billion is what we believe would be the limit of detection, you could actually see that you're still seeing that. Another question that came from Jameson was, we said we could not get the AP4C out of the test enclosure. And was that because of contamination and the fact that we could not decontaminate it? No, decontamination of A-series agents is not all that difficult. When you get into some of those, they're pretty easy to destroy using hydroxides followed by standard decontamination measures. So no, I would be perfectly comfortable decontaminating it. The problem is that we were not allowed to take it out of the confinement, and neither are we allowed. So based upon the laboratory and where it's held, the materials stay within that laboratory and do not come back out. So that instrument went to heaven because it is already in that laboratory, and based upon some different government rulings, anything that goes in that laboratory does not come out of that laboratory. So hopefully that helps, Jameson. But if you do want to see how to decontaminate and destroy A-series agents, if you have the newest version of the emergency response decision support system and you go into the destruction tool and pick chemical, you can pick the A-series agents and that'll walk you through how to destroy each of these. Okay, and then we will go through more answers later, but the testing was done at MRI Global in the United States. Okay, so now we want to just bring you through what do we do in terms of an approach of if we think we are seeing an event that is chemical warfare agent based. So step one is always going to be, are our victims exhibiting symptoms? Because obviously we're not going to be there right when the release is done. So we have to start remembering what our different agents give for different common signs and symptoms. And when we get into those nerve agents, remember that regardless of whether it's a G series, a B series, or an A series, you're still looking at that salivation, lacrimation, urination, defecation, gastrointestinal distress, emesis or vomiting, and then meiosis or the pinpoint pupils. And remember, and this is one of the ways that the UK were so quick to figure out that it was an organophosphate versus a opioid when they had the pinpoint pupils, was because those pinpoint pupils went along with a great amount of oral secretions of salivation. So just remember that as you start working, it wasn't seizures or vomiting or anything that brought them to that realization. It was the fact that there were pinpoint pupils along with salivation. Pharmaceutical-based agents tend to have a lot of that depressed respiration, reduced anxiety, all those things that you would associate with a anesthesia. So, but remember that when you get to the opioid-based ones, you'll also get that pinpoint pupil. So symptomology is a warning, but you have to continue to monitor. The step two is looking around for precursor type materials. So this is the emergency response decision support system. It is a free tool for the US and partner countries, military and civilian first responders. You can register at chemicalcompanion.org. And this will allow you to look up different materials and say, are the precursors there that might be used in the production of the material? Step three is always going to be measuring the flammability. Remember that some of these things are organic aerosols, and that if they are in that dispersed phase, we could very well be seeing flammability hazards as well. So we want to make sure that no matter what type of event we're going to, we're considering LEL and oxygen levels. And so we're still going to bring in our standard 4-gas sensor. So measure for our oxygen concentration as well. And just remember that high levels will have oxygen displacement. Remember also that oxygen displacement should not be used to measure for the concentration of other materials. The reason behind that is most oxygen sensors have what we call a dead band included in them. And that means that as you get to small changes in oxygen concentration, the sensor doesn't respond to those, so that you don't see a fluctuating answer. And so we need to remember that as we get there, we want to keep in mind that those levels aren't going to just jump out and show you. And you'll have a significant change before you actually see oxygen displacement. So step 5, we come in and we measure with our AP4C in the vapor phase. So you know the front end nozzle here is the vapor phase nozzle. To replace that with what I lovingly call the crack pipe, you just pull one out, push the other one in, and the sensor will automatically adjust. But when we're using an AP4C in vapor phase, we're looking on the channels and saying, if it's a P channel, then it's likely a nerve agent. If it's on the nitrogen channel, then we have our choking, blood, blister, and some of our pharmaceutical-based agents. While our A series agents do have nitrogen in them, because of their low vapor pressure, the likelihood of seeing them in vapor phase on the nitrogen channel is nil to none. And you saw that just recently with the video Scott showed. On the arsenic channel, we'll see arsine, lewisite, and some of the mixtures of mustard lewisite. On the sulfur channel, we'll see the blisters. Some of the FGAs will show up there, specifically 208's one that goes there. And then V series agents will also show up there. So they'll show up on the phosphorus. They may go up to about 3 to 4 bars on the phosphorus channel, and then you start to see the sulfur channel responding. And that's because of that sensitivity difference between the 2 different channels. Remembering that you won't get any detection on things like chlorine and phosgene, propofol and sevoflurane, because these things don't contain phosphorus, nitrogen, arsenic, or sulfur. The nice thing about using elemental detection or something like a flame spectrophotometer is it really future-proofs the system. It doesn't give you that unique identification, but it does give you the detection and the monitoring capability at ultra-low sensitivities.
And so what I wanted to show here is some helpful methods for sampling of materials. So there's really 3 major options that we have with it. So option 1 is your preferred method because you're getting much more operationally relevant data to be able to do there. So if a droplet is on a surface and there is vapor that's being produced from it and it's at sufficient, either the temperature or the concentration of the material is sufficient to allow for it to be detected, it'll show up directly on the detector. So one of the things to make sure that you consider a lot of times is most of the cases when you're dealing with a chemical warfare agent, you will get gradients of concentration. Those gradients tend to happen closer to the materials. So the further away you go from the materials, you'll have less and less. So why that's pertinent, especially if they are primarily respiratory type threats with it, if you're standing up and most of the agent has come down and you're going into an area that's been contaminated, it's mostly going to be on the ground unless there's other objects that are high up in the air. So if there are a bunch of objects that are high up in the air, you obviously need to have more caution than if it's a completely open field, for example, and everything is down below. But option 1 is your best information because you're getting real-time information on concentration levels, which then you can use to determine threats and profiles and determine hot zones from gray zones and other things like that based upon the materials with that. We do recommend the use of the ERDSS chemical companion software from the standpoint of if you know what the chemical is and you can take the readings, you can determine concentration levels, TLV, IDLH relative to the bar levels immediately. And so it gives you a lot of operational information in there. If it's at a low enough concentration, so below that 2 parts per billion in the case of an organophosphate that you can't see, The second option is to use headspace method. So what is a headspace method, and I'll explain a little bit more on the next slide, is you put something on top of that, and what happens is that it helps it to increase the vapor pressure, and so not increase the vapor pressure, but more pressure being built up, and therefore the concentration gets greater, and therefore you can sample underneath it. So you allow it to capture underneath, you put some sort of container, so it can be a cup or a funnel or other things like that, put it underneath the device, allow it some time to build up, and then sample it. And then that will, if it's above the trigger threshold in the detector, you'll be able to see that. If that doesn't work, so if it's in a very cold environment, for example, you'll be able to do that. The third option is to introduce it directly into the device using the S4PE or the future system that should be developed in the near future, which is S4PF, which is just a higher temperature heater. So in that case, you take a sample of it and you introduce it into the detector via what we affectionately call the crack pipe, and that allows you to sample it. So you can get into much, much lower concentrations with that and still be detectable. Where you lose is some operational information on what the actual ppm means to you. So it's more an indicative that these materials are present, less so from a standpoint of what the concentration relevance for the device, because you're entering it directly into the device in a controlled manner. Go to the next slide, please. And so just around the headspace, just to let people know with that, so what you're doing is when you have a liquid and it's slowly aerosolizing off, all materials will do that as long as they have some sort of vapor pressure with them. What happens is those materials will be released by containing them into a smaller area. What happens is they release eventually. What happens is they get to a point where they start to condense and go back into liquid, so that reaches their maximum concentration level, but it increases the pressure or the materials that are present to be able to do that. In the case of all of these materials with their vapor pressure and these vapor pressure curves that we were talking about, why they're important is each material, they help determine, are they going to stick around for a while? Are they going to readily off gas with it? And so all of these materials have a temperature dependency. So if they aren't detectable because they're at really low concentrations, or the vapor pressures aren't allowing them to off gas, by increasing temperature, you see that you increase pressure or the amount of atoms that are present, and therefore you're able to detect them with other methods to be able to do that. And so the AP4C kit comes with a heater system to automatically make that happen. Other detectors make that happen internally into the detector through heating them up. With them, it just depends on the nature of the technology with it. The negative of having them internal into systems is that you can't necessarily handle aerosols as a result, but in our case, we are able to handle aerosols or vapors and the standard solution with the device.
Okay, so as Scott just explained, if we can't get it in your vapor phase, then we do have to go to step 5B, which is using your AP4C and the S4PE, or AKA the crack pipe. That will now allow you to start seeing some N-channel detection, so nitrogen channel detection. But remember, again, because of the sensitivity differences, you're going to be seeing up 5 bars already on your phosphorus channel before the nitrogen channel starts to hit. So in parallel, when you hit that second nitrogen channel bar, you're actually going to overload on the phosphorus channel. And so you'll start to see, like you see when you overload the system, you'll actually have that one channel for the phosphorus flashing, and then all the way across the top, you'll have all of the channels hitting on a red bar. And that will mean that you've overloaded the system, and you'll know what concentration you're at based upon what the maximum is for the phosphorus. Now, step 6 is looking at the state of the hazard. So based upon the way we detected it, we can start figuring out which ones of the hazards we're most likely to have come across and why. And so when we start looking at the different interfaces and the amount that was able to come up, it starts helping us pull apart which ones we have. And so we have a table like this that is in one of the white papers, which includes all the chemical warfare agents. This is the overview paper that you'll receive in your email. And that overview paper ends with this chart that just shows you the process that you should follow and what those readings mean in terms of what type of material in the chemical warfare agent matrix you're likely to have come across. and which measure, based upon which way you're measuring it. So whether you're measuring it in gas phase, liquid phase, or as a solid, it's going to start bringing you through each of these different channels and what that may mean. Also remember that those things like chlorine, phosgene, toxic industrials without phosphorus, sulfur, nitrogen, or arsenic, or sevoflurane, which is a liquid-based, pharmaceutical-based agent, are not going to be detected with the AP4C. So you're going to need something else to measure there. And then there's also a table 8 at the back of the white paper that shows you all the different materials of interest, their chemical formula, their vapor pressures and vapor densities, and what you would measure with the AP4C. And you'll see some that have, like table 1, which has phosphorus and nitrogen. You'll see 2 different limits of detection, 1 for each channel. And then it'll talk about whether you can measure it in the gas aerosol interface or if you need to switch to the liquid solid interface. And also other things that you might want to consider. So where chlorine and phosgene aren't detected, you might want to consider an electrochemical cell specific to those, or a tube that can help you. When you get to liquids that have a vapor pressure associated with them, I've gone through and calculated out for you what your maximum headspace should be above that material. So you can see where something like sarin has a maximum headspace of almost 4,000 parts per million, whereas sulfur mustard is down around 145. And so that tells you a lot when Scott was talking about how you don't get enough of a material to come up and be breathed in unless it is dispersed as an aerosol. That's because of this maximum headspace. And we determined that based upon the vapor pressure of each of these threats. So as you come out to the scene, just remember to size up the event scene first. Do not assume that you're going to get some type of warning that this is going to occur. Historically, that warning has always been people exhibiting symptoms. So even if you're in an area where ongoing warfare is occurring, it's generally the symptoms of people which start us down the path of monitoring for this. Because, in fact, in the last use cases, it's always been people first, and then from there we go forward. Secure the area around where something has occurred. If you're outside, minimum of 300 feet. If you're inside, if you can isolate the entire building, great. Oftentimes you can't, but that's going to depend upon the size of the building, its occupancy type, and the ventilation system and how you can isolate that. Ventilate any interior spaces if you can to minimize the effects on others. Continuously monitor for toxic gases and flammable atmospheres, especially as you start to decontaminate and destroy materials. Because remember, for an A-series agent, it's very closely associated with VX in terms of its physical characteristics, but structurally, it's extremely close to sarin. So what does that mean to us operationally? Operationally, if we go to destroy it with something like bleach as our first step, then we might be breaking it down into something like sarin, which instead of being a static threat that doesn't come out and visit us, it becomes a threat that can actually have a much higher vapor pressure. So we went from something that sat on a surface and didn't do a whole lot to something that now is coming out to meet us. Less toxicity, but more availability. And so we have to remember those things. Remember, if you're concerned about the destruction process, please just go to the ERDSS section on destruction and it will walk you through and tell you that for an A-series agent, your best bet is to use a hydroxide first and then do the full destruction, because that hydroxide will force it to cleave in the right place. Initiate your rescue and recovery operations and develop a plan for contaminated remains, because we have to remember that contaminated remains are going to become a problem for many different reasons. Decontaminate those people who have been exposed. Remember that we don't generally use a high flow water-based decontamination process in the chemical warfare agent arena. In this case, it's more of that blot, apply, remove. Blot any excess material that can still be seen. Apply something like RSDL, reactive skin decon lotion, and then remove it after the exposure time of a minimum of 2 minutes up to 2 hours. Okay? Protect any of the evidence and prepare for a criminal investigation. remember that any of these events is going to get an investigation at a minimum from OPCW. So secure the products where possible, and if there are pieces of the container, ensure that those are secured as well. And then, as always, consider any additional risks that may come out to visit. With that, I'm going to quickly switch over and make sure, while I've answered a lot of the questions, I want to make sure that everybody got to hear them. So Juan Morley did ask if we would be able to share the materials via email after the meeting. Absolutely. The materials will be coming out to everybody. You'll get copies of the 2 different application notes, one on detection and monitoring of chemical warfare agents, an overview of all agents, and then the other being an A-series specific application note on some of the newer information we know today. You'll also get a link to this webinar, so you'll be able to go in and stop and run the video at your content. So that will allow you to see the entire presentation along with our wording along with that. And that will likely be up within 24 hours. It does take me a bit of time to pull together the video and information. And that email will come from ProEngine directly. And I already answered Dion and Jameson's questions on how much material was there and then why we couldn't decon. And then Dwayne's was on who and where was the testing performed, and it was at MRI Global in the United States. And then Juan Morley also wanted to know, are the pharmaceutical-based agents more lethal than the agents, the standard chemical warfare agents? And reality is, it depends upon which one. When you get to things like some of the fentanyl, carfentanil type things, they can be more toxic than some of your standard chemical warfare agents. But it just depends upon how much, how it's enforced, and that type of thing. Matt Brinkman had asked if there was an increased potential for these agents with war in the Ukraine. And the only answer we can say is that NATO and others believe that there is an increased potential, mainly upon the discussions and public statements about use of materials and about the Ukraine working with the US and these types of developments. And so it's a misinformation campaign. These things have oftentimes predated the release of materials. And then the other ones, if there's a certificate for participating, I can make one if you need one, but you'll have to email me directly for that. And my email is up here, Christina Baxter at Emergency Response Tips. There is not an extra at, that's a typo. So it's emergencyresponsetips.com. And other than that, unless anybody has more questions, I think we have 10 more minutes before our deadline to finish. But is there anything else, Scott, that you wanted to bring up?
Just one thing that I forgot around just the A-series agents is because we may not know all the variants of it. And if you look at the history of how they've been used, different variants have been used when they are targeted attacks. So the people that are using them tend to follow a similar pattern where they don't replicate the same things. And so just to be cognizant of that, the Russian government is a big user of IMS technology. And so they understand that if you change one atom in that structure, the IMS systems, because they work on molecular weight, will most likely not be able to detect them. And so to be cognizant of that if they are ever used as targeted assassination attempts, and we are using library-based solutions or molecular weight-based solutions, we may not be able to detect them. And so that's the one thing that is a little scary about them, is we have an idea of what they would be, but we most likely don't know everything that's in their arsenal. And so that's just something to take into consideration that I forgot to mention earlier.
Okay, Justin was asking about the ChemPro detect chemical warfare agents. So the ChemPro is another IMS instrument, so ion mobility spectroscopy. The most commonly used is probably the JCAD or the LCD 3.3, mainly because it is used by several militaries. The ChemPro it's another IMS. It has similar issues with temperature and humidity extremes, so just be careful with that. Again, it won't measure as low of a detection as we can here. And also, we do not have any data yet for any of the IMS instruments being able to measure any of the newer threats. So it will not measure a lot of the A series, and it won't measure the pharmaceutical-based agents, mainly because it can only measure vapor phase. So we have to, any of those things that are aerosol, particulate, liquid, that type of thing, you're not going to be able to measure with that. So that's why most people use flame spectrophotometry for these types of things, because it can measure the aerosols and it can measure the solids and liquids, but it can also measure the gases, and it goes across whether, it doesn't matter whether it's a chemical warfare agent, toxic industrial, any of those things. Hopefully that answers your question, Justin. Okay, perfect. And seeing no others, I guess we will say thank you all, and we will get the video to you, and we will also get those application notes out to you. And hopefully you'll never need them, but hopefully you'll also have the information to help you in case we ever got into a point where we needed to be. Thank you again all for your great questions and for participating and for your interest in the work that we do. Have a great day and stay safe out there.